So number one, F composite G of 10. So that's saying 10 gets put into G first, and then that result gets put into F. So for G, it's 2 times 10 over 10 minus 5. That's 20 over 2 times 10 is 20, 10 minus 5 is 5, which is 4. Now that gets put into F. So F with 4 in it is 1 over 3 times 4, or 1/12. So F composite G of 10 is 1/12. Any questions there? Number two, G composite F of 10 is saying we put 10 into F first. So F of 10 is 1 over 3 times 10, or 1/30. That's going to get put into G. So 2 times 1/30 over 1/30 minus 5. 2 times 1/30 is 1/15. 1/30 minus 5 is negative 4 and 29/30. And we have to divide that. So we've got 1/15. Negative 4 and 29/30. Well, 4 times 30 is 120, plus 29 is 149/30. Dividing means we're going to multiply by the reciprocal, so 1/15 times the negative 30 over 149. The 15 and negative 30 cross cancel to give me 1 and negative 2. So that's negative 2 over 149. That's G composite F of 10. So a little ugly going in that direction. How many of you had the first two right? So any questions on those first two? Number three, I want you to take a minute and look at it and see what you can come up with. Remember, the domain. There are limits on the domain. One of them is we cannot square root a negative. There's no roots in either of these, so that's not an issue. We cannot divide by 0 or have 0 in the denominator. Both of these functions, f and g, are fractions, so that appears to be what we're going to be working with. F of g of x, or f composite g of x, remember, is taking f of x and substituting into it the value of g of x. So it's g of x first and then f. So we first look at g. We cannot put in any values into g that are going to make this denominator 0. Well, what would make that 0? That would be x equals 5. So the limits on g, x cannot equal 5. Now we can't put any values into f that would make this denominator 0. In other words, x can't be 0 going into f. But since this is a composite function, we have to look at values of x that would make g of x equal 0. So whatever we put in for x into g of x, we cannot get a result of 0. As we solve that, the only value that would make that equal 0 would be if x is 0. That would make this 0. So x can't equal 0. So we have those two limits on our domain. If we put this in interval notation, we go from negative infinity to the first one there is 0, united with 0 to 5, united with 5 to infinity. That's our domain. That's saying we exclude 0 and we exclude 5. We could do a similar process, by the way, to find the domain of G composite F. We would look at F first to see what limits X there, and then we'd look at G of X to see what limits are values from F that can't be put into it. We're asked to find composites, the composite of F of X. So F of X equals 1 over 3X. To do a composite, remember, we put Y in for X, or put Y in for F of X, and then we exchange X and Y. So this becomes X equals, I don't know why I'm writing so small, 1 over 3Y. And now we have to solve it for Y. To do that, I need to get Y off the bottom of the fraction. So I'm going to multiply both sides by Y. So I have XY equals 1 over 3. And then I'll divide by X. Y equals 1 over 3X. This is what we call a self-inverting function. F of X is 1 over 3X. F inverse of X is also 1 over 3X. H inverse of X. H of X was 5X minus 2. Again, we put Y in for H of X. Then we exchange X and Y. And we'll solve for Y. So we'll start by adding the 2. So X plus 2 equals 5Y. Then we divide by the 5. So X plus 2 over 5 equals Y. And then we'll shift that back into function notation. That was H. So this is H inverse of X equals X plus 2 over 5. If you look at these inverses, by the way, it's actually the steps that would be taken to solve these equations. If I have Y equals 5X minus 2, if I put a number in for Y, I would solve it by adding 2 and dividing by 5. Well, my inverse is to take X, add 2, and divide by 5. That's the steps for solving that linear equation. Okay, and finally, we're asked to find F composite H of X. F of X is 1 over 3X. H of X is 5X minus 2. So this is telling us to take H of X and put it into F. So instead of X, we're going to put in 5X minus 2. This gives us F composite H is equal to 1 over, distributing the 3, we get 15X minus 6. Any questions there? Okay, so just a quick review of functions, inverses, and composites from on Monday. Just to note, there had some technical difficulties with the recording from Monday. I'm working on getting it fixed. Hopefully I have it posted by the end of the week. I'm gonna have to redo some parts of the video. There was no sound in it for some reason. Okay, were there any questions off the homework from Monday that you've seen as you've started working through it? Anything you want me to go through? Okay, well then let's take a peek at the new material for today. We've talked about functions, and we've talked about linear functions. Linear functions there are the powers on x and y are either 1 or 0. Well, the 1 makes sense. We had y equals 2/3 x minus 5. Both of those have a power of 1. Well, where does the power of 0 come into it? Well, y equals 7. That's a linear function. It's a linear graph. But there's no x in it. Technically, that's x to the power of 0. X to the power of 0 is just 1. So 7 times 1 is 7. When we graph that, we can confirm that it's a function. Because on our graph, we go up 1, 2, 3, 4, 5, 6, 7. Y equals 7 is just a horizontal line at 7. And of course, our tests for a function is that vertical line test. And if we take that vertical line and we slide it across that graph, obviously no place where it's going to cross that line, that graph, more than once. Well, also linear is the equation x equals a number. We might have x equals -2 or some other number. If I go to graph that, get this out of my way. Here's -2, there's my line. It's a vertical line, so it's still linear, but it's not a function. Because when I do the vertical line test, well, the line doesn't cross the graph, doesn't cross the graph, doesn't cross it, now it lays right on top of it. So it touches the graph in an infinite number of points. That is not a function. So it's still linear, just not a linear function. Well, today we're going to take a look at the next step above linear, which is quadratic functions. In a quadratic function, oops, if I spell it right, there we go. In a quadratic function, we now have one of the variables, x or y, has to have a power of 2. Typically for functions, we have y has a power of 1, x has a power of 2. Now it might also have a power of 1 in there for x as well, but it has to have a power of 2 and no higher. We've seen that parabola, seen several parabolas, but they all look very similar. There's that U that opens up and curves steeper and steeper as you get away from the turning point. Let's look at some of the parts of the parabola. That part right there where it goes from going down to going up is called the vertex. Well, through that vertex is a vertical line, or if it's a horizontal parabola, it'd be a horizontal line. That line is called the axis of symmetry. We talked about symmetry a little bit, which means an axis being symmetrical means it can be folded about that axis, and one side will lie on top of the other side. Now, I didn't draw this perfectly straight, but if I had, you would see that I could take the left side here and fold it over onto the right side. So that axis of symmetry can be found straight from the vertex. Also, we have these points here in purple. Those are the x-intercepts, but they're also referred to as the roots of a parabola, where it crosses the x-axis. In other words, where y equals 0. When we've solved quadratic equations so far, one of our strategies, we have the square root method, but if we can't just do the square root method, it is to set it equal to 0 and factor. Well, when it's an equation, if it's y equals, we let y equal 0 and factor, and that finds our root. So the equation of a parabola in standard form. Looks something like this. F of x equals a times x squared. Remember we said x has to have the power 2. Let's talk about a for a second. A does two things. One, it determines how wide or narrow a parabola is. So if a is equal to 1, you just get a standard width parabola. Oops, try that again. If a is larger than 1, let's say a equals 3, parabola gets kind of narrow. Let's say a equals 1/4, that parabola can be kind of wide. The other thing that a determines is whether the parabola opens up or down. All three of these over here were positive values of a. If a equals -1, the parabola would open down. Obviously the same width. I'm just taking this one and reflecting it upside down, tipping it upside down. Of course, a equals -3 would make it narrow, -4 would make it wider. So if I go to expand on the standard form of a parabola or a quadratic equation, I start out with f of x equals ax squared. But this means that the vertex is at 0, 0. It's at the origin of the graph. But from there, we can move the vertex. Remember, if I wanted to move the vertex on the graph, let me get my basic graph up here. Let's say there's my basic graph. And here's my standard parabola. So we're going to let just a equals 1 there. If I want to move this over, let's say I want to move it over 4 spots. I want the vertex to be there. So the graph's going to be the same width. Still going to open up. I'm just moving it over 4 spots. That's moving along the x-axis, so I have to adjust the x. And when I adjust the x, I have to do the opposite. If I want to move 4 to the positive direction, I want 4 to behave like 0. It's x minus 4. If I wanted to move it the other direction, let's say I want to move it 2 units this direction, the negative direction, what would my equation be? f of x equals a times, what would I do to x in the parentheses? There you go, plus 2. Plus 2 moves it back 2 spots. So whatever I do to x, the vertex moves the opposite direction, that amount, along the x-axis. To move it up or down, let's say I wanted to move it up 3 units like this. If you recall, I would adjust y. So to move it up 3 units, it'd be y minus 3. Now, because we're using this f of x notation, I don't like to have things over here with the f of x. So I'm going to add 3 to both sides to move that over. So I end up getting an equation of the form f of x equals ax squared plus the 3. So it moves it up 3, moves the whole graph up 3. To move it down, so I want to move it down 2 spots. F of x equals ax squared minus 2. So what we do over here, outside of the x, moves the graph up or down in the same direction that the sign tells us. And the reason it moves in the same direction is because really it should be over here with the y, but we just don't write it in that notation. So it is consistent. If we subtract from the x, we move it that many units to the positive x. If we add to the x, we move it that many units to the negative x. The same as with y. If we subtract from the y, we move it that many units positive on the y-axis. However, we put it on the other side. So even though it's a plus 3, we are technically subtracting 3 from the value of y. So these values that are over here outside of the x move up or down in the same direction as the sign indicates. So if I have f of x equals x minus 2 squared plus 3. Let's get back here. What point is my vertex at? Dawson, what do you think for my vertex there? Yep, that's you. For x, positive 2, and for y? Three, it's the same, perfect. So the vertex is 2, 3. If I have f of x, let's actually do g of x just to denote it. Equals x plus 1 squared plus 5. For my vertex, what do you think for the vertex there, Valerie? Perfect, negative 1, 5. If I have h of x equals 2x minus 3, x minus 3 squared minus 1. For my vertex there, Jack, what do you get? So this tells us where the x goes. Positive 3. Yep. Perfect. 3, negative 1. Note there's a 2 up here on that one. That does not change the location of the vertex. All that means is that that parabola If I draw it out, these parabolas are going to be our normal width. That 2 means it's going to be narrower. If I have P of x equals -3, x squared plus 4. Noah, you out there? What's the vertex for that one? Careful. The positive 4 is correct. There you go. Yeah, it's a little confusing because there's nothing with the x there. Technically, you think of that as -3 x minus 0 squared. So good job. That's 0, 4. And again, that one has a negative number multiplying the x. So what that means is that one's going to open downward, and it's going to be very narrow because of the 3. Looks something like that. So we can go ahead and graph these from this standard equation, standard form. And let's start out, we're going to keep a equal to 1 for an example or so here. So for this first one here, our vertex is at what? Perfect, 2, -3, right there. Now, a is equal to what for this equation? 1, perfect. There's no number in front of the parentheses, so that's really a 1. It's 1 times the parentheses, but we don't need to write it in. So what that means in a quadratic, remember, we're behaving as x squared. So if I move over 1 unit, I move up 1 squared unit. So if I go over 1 squared is 1. I go up 1. I go over 1 here, I go up 1 squared. If I go over 2, however, what's 2 squared? 4, right? So if I go over 2, I have to go up 1, 2, 3, 4. There's my next point. Same in this direction. I go over 2, I have to go up 1, 2, 3, 4. There's another point. So my parabola is drawn through those points. So that is the approximate shape of a parabola where a equals 1. So how does a change that basic shape? Well, let's make a equal 2. That's going to be a common value of a for us. Let's do x plus 1 squared plus 2. First of all, where's my vertex going to be? What do you think, Valerie? -1, +2. Perfect. So now the 2, a equals 2, think of it almost like a slope for a line. Our run doesn't change, it affects the rise. So down here we went over 1, up 1 squared. Well, over here, up here, we're going to go over 1, up 2 times 1 squared. Well, 1 squared is 1, 2 times that is 2. So we go up 2. Go in the other direction, it's the same. We go over 1, we go up 2 times 1 squared, or up 2. When we went over 2, we went up 2 squared, or 4. Now we're going to go over 2, we're going to go up 2 times 2 squared. So 2 squared is 4, 2 times that is 8. 1, 2, 3, 4, 5, 6, 7. Scroll up. 8, right there. Same on the other side. We go over 2, we go up 8. It narrows our parabola considerably. For a equals 2. Let's do f of x equals -1/2 times x plus 3 squared minus 1. For that one, what's our vertex going to be, Jack? Perfect. -3, -1. There's our vertex. So now a equals -1/2 here. And again, we think of that as like a slope. Before we went over 1 and up 1 squared. Now we have to go over 1 and down 1 squared times 1/2. Well, 1 squared is 1 times the -1/2. We go down 1/2. So again, over 1, down 1/2. When we went over 2, we went down 2 squared. Well, now we go down 2 squared, or we went up 2 squared. Now we go 2 squared times the -1/2. 2 squared is 4, times -1/2 is -2. So we go down 2. Do the same over here. So this, now that a equals -1/2, it's opening downward, but it's also a much wider parabola, like that. If I have f of x equals, let's do x minus 3 squared minus 4. I go to graph this. Where's my vertex going to be at? +3, -4. Perfect, right there. If I don't like those slopes, if using the slopes isn't working for me, what I can do is I can solve to find the roots. Remember, the roots are the x-intercepts. And the x-intercepts are where y equals 0. In other words, f of x equals 0. So I can do this as 0 equals x minus 3 squared minus 4 and solve that. See what values of x make that equal 0. Now I've got to do a little work here. I have to multiply the x minus 3 squared. This is where that perfect square trinomial comes in again. Now I know we've used those. We're going to use them over and over throughout the semester. So make sure you're good with them. So this is a binomial squared. It's going to give us a perfect square trinomial. The first term will be this first term squared. So that's x squared. The second term is found by multiplying the two terms and then times 2. X times -3 is -3x, times 2 is a -6x. The third term then is the second term squared. -3 squared is +9. Then of course we got the -4 there. So what we have here is x squared minus 6x. 9 and -4 make +5. We have, the completing the square, we have quadratic formula, but this one is fairly easy to factor. X minus 5, x minus 1. Those multiply to give us the +5, and they will combine on the outside and inside to give us the -6. So we can solve these equations to get our roots. Either x minus 5 equals 0, or x minus 1 equals 0, this one would give us x equals 5. This one would give us x equals 1. So those are our roots, or our x-intercepts. So up here on our graph let's get back here. There we go. At 5 on the x-axis and at 1 on the x-axis gives us our roots. So that helps us to define the width of our parabola. Rather than using that slope, we can use the x-intercepts or the roots. Any questions so far? In your notes, I want you to graph for me f of x equals 2x plus 3 squared minus 2. I want you to graph it. I want you to find for me when you graph it. I want you to label the vertex and the roots. So I'll give you a couple minutes to work on that, see what you come up with. Then we'll go. So as we're working on this one, where is the vertex at? Dawson, where do you think the vertex at? -3, -2, perfect. The roots require a little bit more work. We're going to set the y or the f of x equal to 0, and the rest of this thing has to be worked out, multiplied out. So we're going to start out by doing the x plus 3 squared. I'm going to keep the 2 outside the parentheses. Inside the parentheses, I'm going to square the x plus 3. That's x squared plus 6x plus 9. Remember, x squared is x squared. X times 3 is 3x, times 2 is 6x. 3 squared is 9. And there's the minus 2 out there. We'll distribute the 2. 2x squared plus 12x plus 18. You still have the minus 2 out there. Then we'll subtract the 2. Well, combine the -2 and the 18, I should say. So we've got 0 equals 2x squared plus 12x plus 16. To factor this, remember, one of the first things we always look for is a greatest common factor. And there is one in here. The numbers are all even. So we can factor out a 2. That gives us x squared plus 6x plus 8. And now it's much easier to factor in this form. X squared plus 6x plus 8 is x plus 2 times x plus 4. So we set the pieces equal to 0. 2 can never equal 0, so we don't worry about that one. X plus 2 that'll equal 0 if x equals -2. X plus 4, that'll equal 0 if x equals -4. So those are the roots at -2 and -4. So there's -2 on the x-axis, there's -4. Those are the roots. The roots are -4, 0, and -2, 0. And we get a graph that's a little bit narrower than the last one. So what if our equation is not in this graphing form? How do we find the vertex? What if it is in what's considered to be standard form? F of x equals ax squared plus bx plus c. Well, let's throw some numbers in here and see what happens. Let's just do f of x equals x squared plus 4x plus 7. What we're going to do is we're going to complete the square. We're not completing the square in an effort to solve the equation. We're completing the square in an effort to put this in graphic form. I'm going to put y in for f of x again. Just because it's easier to work with. And remember, when we did completing the square, the first thing we did was we eliminated the constant. That's a positive 7. We're going to go ahead and subtract 7 from each side. So on the left side here with the y, it's pretty much going to become just a place to store our errand numbers that we'll move them back over to the right when we're done. For right now, we have y minus 7 equals x squared plus 4x. So to complete the square, we need to figure out what goes in here. And remember, whatever that value is, the coefficient of x, remember, was the a. 2 times a times that value, I'm going to call it v for now because we already used c, has to equal b, this value, the 4. Well, a is 1 in this case. We'll call that v equals, so 2 times 1 times v equals 4. V, oops, so it has to equal b squared, I should say. Let me try that again. So this is going to be v squared over here. So we solve that. V equals 2. V squared equals 4. So we have to add 4 here to complete this square. So we're going to add 4 over here. So y minus 7 plus 4 is y minus 3. This side is x squared plus 4x plus 4. Now I kind of jumbled myself as I was talking there. Any questions on how we find what value has to go here? It's fairly simple. If a is 1, it's just this number. You divide it by 2 and then square it. If a is not 1, it gets to be a lot more complex. We use this process, which I kind of made it sound more complicated than it is, but so everybody's good at finding that value to complete the square? Okay. So now we group this. X squared plus 4x plus 4, that's x plus 2 squared. We still have y minus 3 over here. Well, we have to get y by itself here, so we can put that back as f of x. So I'm going to add 4 to both sides, or add 3 to both sides. So y equals x plus 2 squared plus 3. Of course, we're going to replace y with f of x. So our vertex there is negative 2, 3. I want you guys in your notes to find the vertex for f of x equals x squared minus 6x plus 2. So I'm going to replace f of x with y. I'm going to get rid of this constant term here. I'm going to subtract 2. So y minus 2 equals x squared minus 6x. Figuring out what I have to add back in there for my constant. Since a is just 1 here, I'm going to take b, the negative 6. Negative 6 divided by 2 squared. Negative 6 divided by 2 is negative 3. Squared is 9, so I'm adding 9 back in there. So this is y plus 7 equals x squared minus 6x plus 9. This is x minus 3 squared. And we subtract 7 from both sides to get x minus 3 squared minus 7. Y is by itself over here, so I'm going to turn it back into f of x. So that is in graphing form, giving us the vertex 3, negative 7. I know it's break time, but I want to show you one more quick example. There's another way to find that vertex. If I give you f of x equals x squared plus 8x plus, oh, let's put in plus 7. Rather than finding the vertex first, I could find the roots first. It's easier to find the roots from this form than it is from the graphing form. Remember, to find the roots, I let y equal 0. Remember, f of x is the y, so I'll put 0 there. X squared plus 8x plus 7. And then I could either use quadratic formula or I could use factoring. This one actually factors fairly cleanly. X plus 7 and x plus 1. So my roots are where one of those or both of those equals 0. So x plus 7 equals 0 would give us x equals negative 7. X plus 1 equals 0 would give us x equals negative 1. So my roots are at negative 7, 0 and negative 1, 0. Well, because of symmetry, this value of a is positive 1. We know this opens upward. Because of symmetry, we know the vertex has to fall on that axis of symmetry. And the axis of symmetry has to be exactly between the two roots. The roots are negative 7 and negative 1. If I add those together and divide by 2, I get negative 4. That's telling me that axis of symmetry is actually the line x equals negative 4. And my vertex has an x coordinate, whatever it is down here, of negative 4. So I just have to figure out what y is. I can go back to my original equation here and put negative 4 in there. F of x equals negative 4 squared plus 8 times negative 4 plus 7. Negative 4 squared is 16. 8 times negative 4 is a negative 32 plus 7. That all adds up to give us a negative 9. So the y coordinate is negative 9. So the vertex is down here at negative 4, negative 9. So there are multiple ways of coming up with the vertex for these parabolas from that standard form of an equation. Okay, I'm a few minutes late for a break, so let's go ahead and take our break. I'm gonna still try to be back at 10:30, but I'll wait for you if you're a little late. So if we want to graph one of these parabolas, let's take a peek. Let's do f of x equals x squared minus 2x minus 3. We could go ahead and find the vertex using that completing the square method. But let's just go ahead and find our roots and work from there. And put in 0 here for y. And factor. Well, that's going to be x minus 3, x plus 1. x minus 3 equals 0 when x equals 3. Bless you. And x plus 1 equals 0 when x equals negative 1. So we have roots here at negative 1 and positive 3 on our x-axis. So what that means is our axis of symmetry is going to be directly between them. So we're just going to take 3 plus negative 1, divide by 2. We're going to average those points together. We get 1 is our axis of symmetry. So x equals 1 here is the axis of symmetry. So we can find our vertex from that by putting 1 back in here for x. So f of 1 equals 1 squared minus 2 times 1 minus 3. 1 minus 2 minus 3 gives us negative 4. So our vertex is at x equals 1, y equals negative 4. If that's not enough to graph this, we can always get an extra point. And any point we get because of the symmetry, if there's a point over here, we know there's a point on the opposite side of the axis of symmetry in the same spot. So the symmetry means any point we get a second point. Well, we can find the y-intercept. Remember, the y-intercept is where x equals 0. In an equation of this form, that's really easy to find. If I put 0 in for x, that's f of 0. That's 0 squared minus 2 times 0 minus 3. It just gives us negative 3. Y equals negative 3. So that point 0, negative 3 is the y-intercept. Now we go 1 unit to the axis of symmetry, so 1 unit on the other side. There's a point on the other side as well. And now we can graph our parabola through those points, like that. Any questions? So these quadratic equations are used for maximizing and minimizing. You might have a function of your profit as a function of units produced or price. Let's do it as a function of price. So x equals the price, the unit price. And as the price increases, usually your profits increase until you hit a certain point where your sales start to drop because of the high prices. So it's below that limit. So we might have f of x here, our profit function is negative x squared plus 5x minus 6. This is a maximization function because it opens downward. How do we open it? No, it opens downward. Well, that's negative. It's a negative 1. The coefficient of the x squared, a, is a negative 1. So that means what we're going to have here is we're going to have a maxima. A maxima is just the name of the point at that maximum point of the graph. So to find that maxima, we find the vertex. The minimum and maximum are always at the vertex of the parabola. So we can factor this. So set f of x equal to 0. We factor. I'm going to factor out the negative 1 first. So this is x squared minus 5x plus 6. Oops, I did that wrong. I should have put, this should have been plus 6 here. Sorry, I wrote that down wrong. So this is going to be x squared minus 5x minus 6 here. And we can factor that piece. We still got the -1. This will be x minus 6 and x plus 1. Those are our roots, or give us our roots. One root would be where this factor equals 0, x minus 6 equals 0 at x equals 6, or this root, x plus 1 equals 0 at x equals -1. Now we don't even need to graph our roots, but we're going to use them to find our axis of symmetry. The axis of symmetry we find by averaging the roots. 6 plus -1 over 2. That's going to be at 2.5. X is 2.5. So now we put 2.5 back into the function for x to find the value of the y value of our vertex. So f of 2.5 equals negative times 2.5 squared plus 5 times 2.5 plus 6. .5 squared is 6.25, so it's going to be a negative 6.25. 5 times 2.5 is 12.5, of course, plus 6. We can combine these. That's going to be negative 6.25 plus 12.5 plus 6 is going to be 12.25. So the vertex is at x equals 2.5 and y equals 12.25. So the maximum value here is at y equals 12.25. Well, these parabolas are useful tools. We can use them for a lot of other functions other than just maximizing and minimizing. One application might be, let's say we're going to fire a cannon. In fact, let's have some fun with it. Let's say you guys get tired of me in class. You're going to shove me in a cannon and shoot me out into the ocean. Now, to simplify this, we're going to put our cannon buried underground. So the top of the cannon is at the surface of the ground. The formula for the height of something fired from a cannon, actually anything launched from the ground, is your initial velocity. V0 means V initial, or V at time 0, times your time that you've been in flight, minus 1/2 times g is the acceleration of gravity, that's 32 feet per second, times t squared. So we're going to fire me out of this cannon with a vertical component of my velocity of 80 feet per second. So that makes the equation describing my height, h of t, is 80 times t. I'm going to combine the 1/2 times 32 here, so that's minus 16 t squared. So here's the big question. How long do I have left to live? Well, I'm going to go splat when I hit a height of 0. So when this equals 0, I'm hitting the ground. Well, we're going to factor this. It's already equal to 0, so let's factor it. Common factor is 16t. If I divide this by 16t, 80 divided by 16 is 5. T divided by t divides out. 16t squared divided by 16t is a negative 1t, or just negative t. So these two factors, either this equals 0, well, 16t equals 0 when t equals 0. Now that makes sense. I'm at the ground at 0 seconds. That's the moment the cannon is fired, I am at the ground. But that's not the one we're looking for. So the other one, 5 minus t equals 0. I'll solve that by subtracting the 5. Negative t equals negative 5. And we'll divide by negative 1. So t equals positive 5. So that's saying is I'm going to get back to the ground at a height of 0 in 5 seconds. So 5 seconds from liftoff, I am going splat. We can maximize this. Let's say we have 80 feet of fence to enclose a pasture, or to enclose a pen, I should say. That wouldn't be much of a pasture. Find the maximum, the largest area. So in a fence, we're going to have a length and a width, right? Of course, there's going to be two of them. This will be the length and this is going to be the width. The area is length times width. Well, we know that the length times, or length plus width, is half of the perimeter because there's two lengths and two widths here. So the length plus width is going to be half of our 80 feet of fence. The length plus width has to add up to 40 feet. Because we have the other 40 feet does the other length and the other width. So what we're going to define here is our area as a function of our width, or as a function of our length. So it's length times the width. If I solve this, if I subtract the length from each side, the width is 40 minus whatever the length is. So I get that equation. Area equals length times 40 minus the length. And I want to maximize this. So that means I'm going to find that local maximum or minimum. Well, my roots here are the length equals 0, this equals 0, or 40 minus the length equals 0. That would give us L equals 40. Those are my roots. So my axis, and therefore my vertex, have an x coordinate that's somewhere in between there. In fact, it's exactly in between there. 0 plus 40 over 2 is 20. So at the vertex, x has a value of 20. So to find the value of y, the area, L is 20 times 40 minus 20. That's 20 times 20, or 400. So the vertex is this, is at x equals 20 or L equals 20, area equals 400. 400 is the maximum area. So that's the largest possible area that could be enclosed by 80 feet of fencing. Okay, so other functions. We talked about linear functions where x has a power of 1 or 0. Quadratic functions where x has a power of 2. As we get larger than that, and there's a cubic function where x has a power of 3. But rather than splitting them up into each power, we're just going to talk about polynomial functions. Now, technically, our quadratic functions and our linear functions are polynomial functions. First degree, that means x, the largest power on x is 1. That's linear. We've already done those. Second degree, meaning the largest power on x is 2. That's a quadratic, giving us the parabolas that we just talked about. So we're looking at polynomial functions, but we're really only looking at the ones that are larger than second degree. So a polynomial function is a function of the form f of x equals a to the n, a sub n times x to the power of n plus a sub n minus 1. There's different powers of, since we don't know how many terms there are, rather than labeling them a, b, c, d, we just use a with different subscripts. Times x to the power of n minus 1 plus, this will count down times to a2 times x squared plus a1 times x to the power of 1 plus a0. Technically, this is times x to the power of 0, but we don't have to write that in because x to the power of 0 is 1. And there are a lot of properties of these polynomial functions. One property is they always form a smooth curve. They're not going to have any like sharp corners or anything like that when we graph them. Second, we're going to talk about end conditions. They either go to infinity or negative infinity at each end. If we look at our linear functions, that makes sense. A line graphed, as we go to the positive side here, this is getting larger and larger. That's going to go up to positive infinity. And the negative side, that's going to go to negative infinity. That's if we had a positive slope. If we had a negative slope, same thing. Goes down to negative infinity here and up to positive infinity. A parabola, same situation. If that's first term, if a is positive, it shoots up to negative infinity on both ends, or shoots up to positive infinity on both ends. If a is negative, it shoots down to negative infinity on both ends. So there's end conditions. Either end of a polynomial graph shoots either up to positive infinity or down to negative infinity. And we'll look at how to determine those. And then there's roots that we're going to talk about. How many roots do they have? Well, let's talk now about the end conditions. What are those? How can we look at those? So those end conditions are determined by that coefficient of the largest power. So that a to the n, or a sub n, that was in our generic form. If it's positive, we have to look at our degree of the equation. If it's an odd degree, the left side is going to go down to negative infinity. The right side, in other words, the positive x, is going to go up to positive infinity. So we're going to get a graph that looks something like this. If it's an even degree, so that power is a 2, 4, 6, or 8, they're both going to shoot up to positive infinity. Think about this. In a parabola, if a was positive, they both went up. If a was negative, they both went down. So that brings us to if an is negative. If that degree is odd, these are just switched. On the left end, it shoots up to positive infinity, and on the right end, it goes down to negative infinity. If it's an even degree, both shoot down to negative infinity. So if I have f of x equals negative 3x to the fifth minus 7x to the fourth plus 2x to the third plus 5x squared minus x plus 9. There's my an. That's the coefficient of the largest power of x. It is negative. This is an odd degree. It's the fifth power. So that means is when I graph this, I'm expecting the left end to shoot up to positive infinity, my right end to shoot down to negative infinity in some form. Now the shape in between there, I'm not totally sure of, but we'll get to that in a second. So we mentioned, so that's our end behavior. Our roots. The number of roots is either equal to the degree or the degree minus an even number. I was going to write the degree minus 2k, where k is an integer, or k is a whole number, but same thing. So this up here had a degree of 5, So my roots, there's either going to be 5, 3, or 1 root. Remember, roots are that x-intercept, so it's going to cross the x-axis either 5 times, 3 times, or 1 time. So if I have the function f of x equals 5x to the third minus 2x squared plus 20x minus 8. I know that's going to have 3 or 1 root. And those roots are going to be found when the y value equals 0, or f of x equals 0. Well, how do I find those roots? Just like before, just like a quadratic, we factor. Now this has 4 terms, so we're going to try to do grouping. We'll group the first 2 terms and the last 2 terms and look for common factors in those groups. Well, in this group, we've got a common factor of x squared. So that's x squared. What's left would be 5x minus 2. In this second grouping, we got a common factor of 4. I divide out the 4, I have 5x minus 2. If you recall from factoring by grouping, that's our goal, is to get the same expression inside both sets of parentheses. Are there any of you that don't remember how to do factoring by grouping? Okay, good. So then once we have the same thing inside both sets of parentheses, we factor that out. So we get the 5x minus 2 pulls out, and what's left there is the x squared. Oops, I screwed that up, plus 4. The x squared plus 4 can't be factored because it's positive. If we try to solve each of these, 5x minus 2 equals 0. We would add 2, 5x equals 2, and divide by 5. X equals 2/5. That's one of my roots. If I try to solve the other one for 0, x squared plus 4 equals 0, well, I can try the square root method. I subtract 4, x squared equals negative 4, but if I try to square root that, square root of negative 4 can't be done. It's going to be imaginary. That's going to be the positive or negative 2i. Remember, we used I for that square root of a negative number. So there's 2 roots there, but they're imaginary. So they don't appear on our graph. So when we graph this polynomial function, it's only going to cross the x-axis once, and it's going to be at 2/5. So between 0 and 1. Now, end behavior. A here is positive. AN is positive. And our degree is 3, so that's odd. So that means It shoots to negative infinity on the left side and positive infinity on the right. So it means when we go through this rut, we're going to be going through in that direction. It's going to increase. Where the other rut is, there's going to be an inflection point of some point. But we know our graph comes up here somehow like that. We don't know how it continues, but we know that much about it. Well, what if it doesn't factor as neatly as this did? And we're looking for those factors. Well, we know we are looking for roots, either 3 or 1 root here. So we know there's at least one real root. And what we can do is we can try values. If we try values for x into that function, let me get that function again so I remember what it was. Five, -2, 20, and -8. Let's say, because it's an easy one to calculate, let's calculate f of 0. F of 0 would be 5 times 0 to the third minus 2 times 0 squared plus 20 times 0 minus 8. Well, it's pretty easy to see that all those terms are 0. That just equals -8. So that gives us the point on the graph of 0, -8. If I try x equals 2, f of 2, well, that'll be 5 times 2 to the third minus 2 times 2 squared plus 20 times 2 minus 8. Well, 2 cubed is 8, so that's 5 times 8. 2 squared is 4, so that's 2 times 4. Five times 8 is 40, minus 2 times 4 is 8. 20 times 2 is 40, minus 8. If I add that up, I get 64. So at x equals 2, y is 64. Now you might be looking at these 2 points here thinking, so what? What do they tell us? Well, when x is 0, y is -8, and when x is 2, y is 64. Here, the y value is negative. Here, the y value is positive. Whenever the value of y on our graph goes from positive to negative or negative to positive, somewhere between those x coordinates, so somewhere between x equals 0 and x equals 2 is a root. Now we've already found that root. That root is at x equals 2/5. But we know there has to be a root in between those. That's called the intermediate value system, intermediate value theorem. And all it says is if f of a is positive and f of b is negative, there is a root somewhere between a and b on the graph. Our turning points. This is a feature we haven't discussed yet. A turning point is slope either goes positive to negative or negative to positive. In other words, the graph goes from being increasing to decreasing or from decreasing to increasing. The point where it does that is called a turning point. So there's a turning point, there's a turning point. The number of turning points is either going to be the degree of the graph minus 1, or that degree minus 1 minus an even number. So just like our number of roots, it's either that amount or 2, 4, 6, 8 less. Same with our turning points. So this one that we've been working on here had a degree of 3, so there's either 2 turning points or 0 turning points. So what that means is that graph comes up, so a degree of 3, so these are 2 or 0 turning points. So either it comes like that, where there's 2 turning points, or it doesn't quite get a turning point, like that. Now we will discuss, of course, one of the things about a turning point is the slope at that point equals 0. That's one of the big things when you move on to calculus is going to be looking at how do you define the slope of this function at every point. And if you can find the points where the slope equals 0, you found the turning points. Or vice versa. If you found the turning points, you found the points where the slope equals 0. And of course, between these turning points, the slope is negative, and on either side, it's positive. Okay, so homework 3B, which was assigned on Tuesday, is due tomorrow. Quiz 3, which is on homeworks 3A and 3B, is due Friday. And homework 4A is going to be due next week, Tuesday. Now that's homework 4A already. Remember, in week 5, we will have our next unit test. So what is that coming up, I believe, on October 7th should be our unit test. So be ready for that coming up. Any questions? Okay, well, you guys have a great day. Have a great weekend, and we'll see you next Monday.